Why does fire burn? It seems like the simplest question you could ask. You strike a match, flame appears, heat radiates outward, and something we call burning happens. But if I ask you what's actually occurring at that moment, what would you say? That the wood is being consumed, that energy is being released. These answers feel satisfying until you press deeper. What does it mean for wood to be consumed? Where does it go? And what is energy? Really, that it can be released from matter as if it were trapped inside. The truth is that most people walk through life surrounded by fire without understanding what it is. They see flames and feel heat and assume they comprehend the phenomenon, but they don't. And here's what's remarkable. Once you truly understand fire, you'll realize that almost everything you thought was solid and permanent about the world is actually a temporary arrangement of processes. Fire isn't destroying anything, it's rearranging reality. Let's start with what we observe. You take a piece of wood and light it. The wood glows, produces heat, and gradually turns into ash. The naive view is that fire consumes the wood, turning it into nothing. But that violates a principle we've known since Lavoisier in the 18th century. Matter is conserved. Nothing is created or destroyed in chemical reactions. So where does the wood go? Here's the key insight. Wood isn't disappearing, it's transforming. The wood is made primarily of cellulose, a complex molecule built from carbon, hydrogen, and oxygen atoms. When you burn wood, you're not making it vanish. You're breaking those molecular bonds and allowing the atoms to recombine with oxygen from the air. The carbon in the wood combines with oxygen to form carbon dioxide. The hydrogen combines with oxygen to form water vapor. These gases rise into the air invisible, carrying away most of the wood's mass. What remains as ash is a small fraction of minerals that were always in the wood but couldn't vaporize. So the first revelation is this: fire doesn't consume, fire rearranges. It takes complex molecules and breaks them into simpler ones, releasing the atoms to form new combinations. The wood never disappears. It simply becomes gas. But now we must ask a deeper question. Why does this process produce heat? Why does rearranging atoms release energy that we can feel as warmth and see as light? This is where the real physics begins. Every chemical bond between atoms contains potential energy. When atoms bond, they settle into a lower energy state, and the difference is released. Think of it like a boulder sitting on a hill. The boulder has gravitational potential energy because of its position. If it rolls down, that energy converts into kinetic energy, motion. Chemical bonds work similarly. When carbon and oxygen are separate, they have higher potential energy than when they're bonded together as carbon dioxide. The carbon-oxygen bond in carbon dioxide is very stable, very low energy. So when carbon atoms from the wood encounter oxygen molecules from the air, they bond, dropping into a lower energy state. The energy difference has to go somewhere. It becomes heat and light. This is the essence of combustion. It's an exothermic reaction, meaning it releases energy. But notice what's actually happening at the molecular level. The wood's complex molecules require an initial input of energy to break apart. That's why you need a spark or flame to start a fire. Once started, the breaking and reforming of bonds releases more energy than it consumes, and this energy sustains the reaction. Heat from the flame breaks more molecular bonds in the wood, which react with oxygen, releasing more heat, which breaks more bonds. It's a self-perpetuating process. Now here's something critical that almost no one appreciates. When we say fire produces light, we need to understand why. The atoms involved in combustion don't just release energy as heat, they release it as electromagnetic radiation. Electrons in the atoms get excited by the energy of the reaction. They jump to higher energy levels, then fall back down, emitting photons as they return to their ground state. The wavelength of these photons determines the color. A candle flame is yellow because the temperature excites electrons enough to emit light in the visible spectrum. Predominantly yellow and orange wavelengths. Hotter fires burn blue because higher temperatures mean more energetic photons. Shorter wavelengths. Fire, then, is not a thing. It's a process. It's the visible evidence of rapid oxidation, a chemical reaction between fuel and oxygen that proceeds fast enough to produce heat and light. The flame you see is glowing gas, heated particles of soot and vapor radiating energy. There's no substance called fire. There's only matter undergoing transformation, and the light we perceive is the signature of that transformation. Let's go deeper into what's happening at the atomic scale, because this is where the picture becomes truly precise. When we say oxygen reacts with carbon, we need to understand what a chemical reaction actually is. It's not magic, it's quantum mechanics. Atoms consist of nuclei surrounded by electron clouds. These electrons exist in specific orbitals, regions of space where they're likely to be found. Chemical bonds form when atoms share electrons, and whether a bond forms depends on the energy configuration. Electrons naturally seek the lowest available energy state. When a carbon atom encounters two oxygen atoms, the system can lower its total energy by forming carbon dioxide, a molecule where electrons are shared between carbon and oxygen in a stable arrangement. This new configuration has less energy than the separated atoms, so the reaction happens spontaneously once there's enough energy to overcome the activation barrier. The activation energy is crucial. Even though burning releases energy overall, you need energy input to start the process. Why? Because breaking the initial bonds in the wood's molecules requires energy. The cellulose molecules are stable. Their atoms are held together by covalent bonds, sharing electrons in configurations that resist disruption. You need heat to make those atoms vibrate energetically enough that bonds break. Once broken, the atoms are free to recombine with oxygen, and that recombination releases even more energy than was needed to break the original bonds. This excess energy heats nearby molecules, breaking more bonds, sustaining the reaction. This is why fire spreads. It's not that fire moves. The chemical reaction propagates because the heat from one region provides activation energy for adjacent regions. Fire is a chain reaction, a cascade of molecular transformations where each step enables the next. Now consider oxygen's role more carefully. Oxygen is unusual. It's a powerful oxidizer, meaning it readily accepts electrons from other atoms. This is because of oxygen's electron configuration. It has 6 electrons in its outer shell but wants 8 for stability. When oxygen bonds with carbon or hydrogen, it effectively gains those electrons, achieving a stable configuration. The drive towards stability is what makes oxidation energetically favorable. Nature prefers lower energy states, and oxygen-containing compounds often represent those lower states. Here's a profound point. Burning is just rapid oxidation. The iron in your car rusts through oxidation too, combining with oxygen to form iron oxide. But rusting happens slowly, releasing energy so gradually you don't notice heat. Fire is the same process accelerated. The fundamental chemistry is identical. In both cases, atoms rearrange to form more stable configurations, releasing energy. The difference is only the rate. This raises a philosophical question. If fire is just chemistry, just atoms following quantum mechanical rules, then what about other phenomena we experience as distinct? What about life? Your body oxidizes glucose in your cells through a process called cellular respiration. You're burning fuel, combining it with oxygen, releasing energy. But it happens in controlled steps, mediated by enzymes, so the energy emerges as useful chemical energy rather than heat and light. The distinction between metabolism and combustion is one of control, not fundamental principle. You are, in a precise sense, a very slow, very controlled fire. Let me address a common misconception. People often think fire needs air. That's not quite right. Fire needs oxygen, specifically, not air. Air is mostly nitrogen. About 78%. Nitrogen is inert under normal conditions. It doesn't participate in combustion. What fire requires is the oxygen in air, about 21%. In pure oxygen, things burn far more intensely. In pure nitrogen, they don't burn at all. This tells us something important. Combustion is chemically specific. It's not about exposure to any gas. It's about the presence of an oxidizer. You can also have combustion without oxygen if you use another oxidizer. Chlorine, fluorine, other reactive elements can support burning. The key is having a substance that accepts electrons, allowing fuel molecules to reach lower energy states. Oxygen is common and effective, so we associate it with fire, but the principle is broader. Combustion is any rapid exothermic reaction between a fuel and an oxidizer. Now let's think about the flame itself, the visible part. What are you actually seeing? A flame is a region of reacting gases, heated to incandescence. The heat excites molecules and atoms, causing them to emit light. Different parts of the flame have different temperatures and different chemistry. The base of a candle flame, near the wick, is relatively cool and contains vaporized wax that hasn't fully reacted yet. The middle region is hotter and yellow, glowing from incandescent soot particles, tiny bits of carbon that haven't yet oxidized completely. The outer edge, where the flame meets abundant oxygen, is the hottest part and often appears blue. Blue light means higher energy photons, which means higher temperature dot. The shape of a flame is determined by convection. Hot gases are less dense than cool gases, so they rise. This creates the characteristic upward teardrop shape of flames in Earth's gravity. In microgravity, without convection, flames are spherical. They radiate heat outward evenly, and fresh oxygen diffuses in from all directions. This shows that flame shape isn't intrinsic to combustion. It's a consequence of gravity and fluid dynamics. We need to examine energy more carefully now because the concept of energy release is where most people's understanding becomes vague. What does it mean for energy to be released during combustion? Energy is conserved. It doesn't appear or disappear. It only changes form. So when we say burning releases energy, we mean that chemical potential energy converts into thermal energy and electromagnetic radiation. Let quote says. Quantify this, the chemical potential energy in a molecule is the energy stored in its bonds, determined by the electromagnetic forces between electrons and nuclei. When bonds break and new bonds form, the total energy changes. If the products have lower potential energy than the reactants, the difference must emerge as other forms of energy. In combustion, it emerges primarily as kinetic energy of molecules, which we perceive as heat, and as photons, which we perceive as light. Consider the reaction at the molecular level. A methane molecule, one carbon atom bonded to 4 hydrogen atoms, encounters 2 oxygen molecules. The existing bonds break, requiring energy input. New bonds form, creating carbon dioxide and water, releasing more energy than was required to break the original bonds. The net energy release per methane molecule is specific and calculable. For methane, it's about 890 kilojoules per mole. This number comes from measuring the bond energies involved. The carbon-hydrogen bonds in methane have certain strengths. The carbon-oxygen and oxygen-hydrogen bonds in the products have different strengths. The difference is the energy released. This energy doesn't emerge slowly. It emerges at the speed of molecular collisions. When a carbon dioxide molecule forms and drops into its lower energy state, the energy releases almost instantaneously, transferring to nearby molecules as kinetic energy. These molecules move faster, colliding more energetically, heating the surrounding gas. This is how fire generates heat. It's the microscopic kinetic energy of countless molecules, all moving more rapidly because of the energy released by chemical reactions. The temperature of a flame depends on how much energy each reaction releases and how quickly that energy can dissipate. A flame in pure oxygen burns hotter because more oxygen is available per unit time, allowing more reactions, more energy release. A flame in confined space might burn cooler because heat dissipates slowly, but it might also burn hotter if oxygen is still available, concentrating the energy. Temperature is a statistical measure of molecular kinetic energy. Hotter means faster moving molecules on average. Now think about what this means for matter itself. The wood you burn was once part of a tree. That tree built its structure from carbon dioxide in the air and water from the ground, using energy from sunlight. Photosynthesis is the reverse of combustion. Plants take carbon dioxide and water, add energy from light, and produce glucose and oxygen. They're building high-energy molecules from low-energy ones, storing solar energy in chemical bonds. When you burn wood, you're releasing that stored solar energy. The sunlight that fell on leaves years ago is now warming your hands. The carbon atoms in the carbon dioxide released from your fire are the same atoms the tree pulled from the air. Combustion closes the loop. This reveals something profound. The atoms in wood and air and you, they're not static. They're constantly cycling through different forms. Carbon atoms move from carbon dioxide in the atmosphere into plants through photosynthesis into wood, then back into carbon dioxide through combustion or decay. Oxygen atoms cycle through air, water, organic matter, and back to air. Hydrogen cycles through water, organic molecules, and back to water. Matter is not permanent stuff. It's a flow, a circulation of atoms through temporary structures. Fire makes this visible. When you watch a log burn, you're watching atoms rearrange themselves from one temporary form into another. The log seems solid and permanent, but it's not. It's a collection of atoms held together by electromagnetic forces in a particular configuration. That configuration is stable for a while, but it's not the lowest energy configuration available. Given a chance, given activation energy to overcome the barrier, those atoms will rearrange into carbon dioxide, water, and ash, releasing energy as they drop to lower energy states. Fire is the transition. It's the process of matter seeking equilibrium. Here, quote, is another way to see it. The universe tends toward disorder, toward entropy. Organized structures like wood molecules represent low entropy, high order. The products of combustion, carbon dioxide and water molecules dispersed into the atmosphere, represent higher entropy, more disorder. The second law of thermodynamics tells us that in any isolated system, entropy increases. Fire is entropy in action. It's the universe dismantling organized structures and spreading energy and matter more evenly. The heat you feel from fire is the tangible manifestation of entropy increasing. But entropy isn't destruction, it's transformation. The atoms don't vanish. The energy doesn't disappear. Everything simply becomes more dispersed, more disordered, more evenly distributed. Fire doesn't destroy reality. It reveals reality's fundamental tendency toward equilibrium. Let's address the question directly now. Why does fire burn? The answer is that fire doesn't burn. Burning is a word we use to describe a set of chemical reactions, specifically rapid exothermic oxidation, but there's no entity called fire that performs this action. There's only matter, atoms and molecules following the laws of quantum mechanics and thermodynamics. When conditions allow, when fuel and oxidizer meet with sufficient activation energy, atoms rearrange themselves into more stable configurations. We call this phenomenon fire and we say it burns, but what's really happening is chemistry. Atoms are bonding and releasing energy, following principles that govern all matter everywhere. Why does this matter? Because once you understand fire at this level, you understand that almost everything you perceive as solid and stable is actually dynamic and temporary. The chair you sit on is made of molecules that are thermodynamically unstable. Given enough time or the right conditions, they'll decompose, oxidize, transform. The only reason they persist is that the activation energy for their transformation is high enough that the process occurs slowly. But make no mistake, the chair is not fundamentally different from the burning log. Both are collections of atoms in temporary configurations. One configuration changes quickly, the other slowly, but both are subject to the same underlying physics. This perspective extends to everything. Your body is a complex chemical system where reactions occur continuously, controlled by enzymes and cellular machinery. You're not a static object. You're a process, a flow of matter and energy maintaining a temporary pattern. The atoms that constitute you today are not the atoms that constituted you 10 years ago. You've been replaced atom by atom, yet you persist as a pattern. Fire is the same. Fire is not a thing, but a pattern of reactions, a wave of transformation moving through matter. Consider the broader implications. If fire is chemistry, and chemistry is atoms following quantum mechanical rules, then fire is fundamentally predictable. Given complete information about the molecules involved, their configurations, their energy states, and the environmental conditions, you could calculate exactly how the fire will proceed. You could predict the temperature, the rate of combustion, the products formed. There's no mystery, no special fire substance. There's only atoms obeying laws. Yet we experience fire as something primal and elemental. Humans have revered fire for hundreds of thousands of years. It provided warmth, protection, the ability to cook food. Early civilizations considered fire one of the fundamental elements, a basic building block of reality. But fire isn't an element. It's not even a substance. It's an event, a transformation. Understanding this doesn't diminish fire's importance. It enhances it. Fire is significant precisely because it represents the principles that govern all change in the universe. Here, quote, the deepest point. Fire teaches us that the distinctions we draw between things are often artificial. We see wood and ash as different, but they're made of the same atoms in different arrangements. We see matter and energy as separate, but energy is just a property of matter's configuration and motion. We see ourselves as distinct from the environment, but we're made of atoms that came from stars, that cycle through air and water and organisms that will eventually disperse back into the cosmos. Fire is the visible reminder that boundaries are permeable, that forms are temporary, that reality is flux. When you watch a flame, you're witnessing quantum mechanics in action. You're seeing electrons changing energy levels and emitting photons. You're watching thermodynamics as entropy increases. You're observing chemistry as molecules transform. And you're seeing in miniature the same processes that power stars, that drive life, that shape the universe. Fire is not separate from these grand phenomena. It's the same physics operating on a scale we can perceive directly. So why does fire burn? It doesn't. Matter transforms according to physical law. Atoms seek lower energy states. When conditions permit, they rearrange, releasing energy we detect as heat and light. We've given this process a name, burning, and the visible manifestation, another name, fire. But names don't create reality. They only label it. Fire is not doing anything to reality. Fire is reality, expressing itself through chemistry. The final insight is this. Understanding fire doesn't remove its beauty or power. It deepens both. When you understand that the warmth of a fire is the kinetic energy of molecules, that the light is photons emitted by excited electrons, that the entire process is atoms seeking equilibrium, you're not reducing fire to something mundane. You're recognizing that the mundane is extraordinary. The universe operates by precise, comprehensible principles, and those principles produce everything we experience. Fire is not magic, but the fact that chemistry and physics produce flames, that matter can transform and release energy, that we can understand these processes through reason and experiment, that is profound. That is the true wonder. Not that fire burns, but that we can understand why.